Hello everybody. Welcome to the third and last video of the ones that I'm going to be producing for YouTube, um, aka the only real reason I have to shower and shave and get dressed and stuff in light of the situation that's going on. And hopefully you found these replacements for lectures pretty useful at the end of the day. It's been an interesting time, eh? Yeah, today we're going to finish the conversation about numerical integration. We have covered Riemann sums. We have covered um, trapezoid rule. And this is different sorts of ways of approximating where Riemann sums, of course, are adding up areas of rectangles, where trapezoid rule is improving that scheme by instead considering areas of trapezoids. Simpson's rule actually gives us yet another method. You might be asking, how can you do much better than that? But in fact, there are all sorts of different numerical approximation schemes that go even beyond what trapezoid rule does. These are different schemes. I think I used the word last lecture called quadrature, and there are different kinds of quadrature methods that do a different job. If you're working on finding a topic for your project at the end of this course, it might be useful to look into one of those, especially if you've liked this kind of material. Today, though, Simpson's rule. Let's talk. So, let's get this pen together. So, yeah, we know that Riemann sums give us an estimate of a definite integral by using rectangles. But if you think about that, that's essentially taking a function of whatever that looks like and approximating it by a piecewise constant function instead and finding the area under that. And so that's the general idea behind a Riemann sum, where trapezoid rule takes instead a piecewise linear function as we connect the dots between each node. But if you think about that, that kind of leans toward, okay, if we go to for constants for Riemann sums and then linear for trapezoid rule, maybe an extension of that is to consider doing something like using parabolas, i.e. maybe there's a way to use a collection of quadratics to provide an even better approximation. And that motivates the rule that we're going to finish off with here in this section, which is Simpson's rule. So if we scroll on down to the next page here, let's do this. So we're still working on this same integral, okay? Just a definite integral between a and b, that's our domain of integration, and we need the right continuity and so on to make sure that that is well defined. Okay, we're going to discretize this, the a to b, that interval, into three nodes. And we're just going to do three nodes, period, to start. It's hard code something, but we're going to extend from there before the end of this, okay? So x0 is going to be the left endpoint, okay? The a. x2 is going to be the right endpoint. x1 is going to be equally spaced between the two. It's got to be the average of the two. x1 is going to be a plus b over 2. Okay, so we have three evenly spaced nodes. And what we're actually going to do is jump back to something from earlier in the course, back in week 4 and 5, or 5 and 6, I don't know, whenever we talked about polynomial interpolation, and use that, okay? We can talk about the Lagrange interpolant for these points. You remember how that works, right? We have to find those basis functions and then lift those basis functions up to the right height. Let's do a little bit of work here just to remind you how that works. It'll be good practice for the exam anyway, right? We would construct three basis functions of the following. I'm going to call them L0, L1, L2 because why not? To go with x0, x1, x2. But I would have here L0 is equal to, well, how did that work again? I need to take x minus x1, um, x minus x2 over x0 minus x1, x0 minus x2. And we do that same sort of pattern for all three of those basis functions, if you remember. So we can construct two others that are very similar, x minus x0 over x minus, or sorry, times x minus x2 over x1 minus x0 x1 minus x2. And I didn't really leave myself enough room here, but let's see. Maybe I'll just write it right here. L2 would be x minus x0, x minus x1 over x2 minus x0, x2 minus x1. Okay, and we have the x0 and x1 and all that kind of stuff defined up above, so we could rewrite these if you really wanted to. Um, but at the end of the day, we would have p of x equaling, it would be the height times the correct basis functions for each one of those nodes. So I would get here f of x0 times L0 plus f of x1 times L1 plus f of x2 times L2. And I know that x0 and x1 and x2, those are just going to be as they're defined above. So maybe I'll just write that in green below to remind you that we could go and fill all that stuff in. So with x0, x1, x2 defined as above. Okay. Well, so what are we going to do with this, right? That would be a whole scramble of different points and functions being evaluated and so on. But in the end, it looks like we're going to get parabolas, right? X minus x0 times x minus x1 is just a quadratic function. I have two x terms, right? The other stuff is just constants. And I'm adding up three of those parabolas. So this is the unique polynomial that would go through those three nodes. And yeah, essentially the way that this is going to work is that the true area underneath the curve, thinking of those definite integrals in terms of area, is going to be, well, if the parabola well approximates the curve, then the area underneath the parabola is going to well approximate the area underneath the curve, the true area, right? So if the resulting quadratic is a good approximation of the curve, then the associated area under it should also be a good approximation of the true area. So the area I'm thinking of as being that definite integral. It's well approximated. If I can't integrate the f, I can certainly integrate a quadratic, right? And that's all the p of x is. So if I have a quadratic there, then maybe that's something that we can do. And you can do a whole derivation for this, and it leads to a formula. I didn't go into the details there because it is kind of messy, and it's just slogging around a bunch of variables and so on, right? Like, we know how to integrate a quadratic function, but imagine having to, do it generally and weeding around with the notation and stuff. So we want a general formula. So doing that work, you could go through. I have done it in the past, but it's like a couple of pages and it's kind of beside the point. So I leave that as an exercise if you really want to try it out. But regardless, it's going to all reduce at the end of the day to a formula that looks like what's at the bottom of the screen right now. So you're going to take that difference between the x2 and the x0, the a and the b, or the b and the a, I guess. You actually divide by 6. And then what happens is you get this f of x0 plus 4 of the middle plus f of x2. It's a little bit interesting. That's just how it turns out to work. And we're going to use that on an example, okay? So, typically, right, like if you're considering a uniform subinterval, you can change this around because if in that case, x2 minus x0, well, if you've evenly spaced the three the 3 points, then each one's going to have a width of x2 minus x0 over 2 for the two subintervals. And so that quantity is equal to h, and if you do the math, a little bit of arithmetic, you can express in terms of the h instead, which is what we're typically going to do, right? You instead get h over 3 times that same quantity. So this is the formula that I want you to know, this one right here, okay? And this is going to be Simpson's rule for 3 nodes. notice that we need 3 nodes here. We need 3 nodes, otherwise we literally can't construct parabolas. So this is an interesting method in that it requires exactly 3 nodes, although we're going to extend it to more after this example, but we can't do less, okay? So, oh yeah, there was a guy named Thomas Simpson, I guess, who used it in the 1700s, which is where this the name comes from. So we're going to use Simpson's rule to approximate the value. Give it in this integral right here. It's another special function. You can't do this by hand. You have to go to an approximating technique, and so we're going to use Simpson's rule for this. So let's start with some basic information here. We want to use 3 nodes here. Oops. And if we have 3 nodes, that's going to be, if they're equally spaced between 1 and 2, 1 and 2 are 2 of the nodes, and the third's going to be 1.5. So let's write that down. So x0 will equal 1, x1 will be 1.5, and x2 will be 2 with, of course, the h in that case will be 0.5. Okay, and it's really just a matter of working with that that formula above. We just need h over 3, and then we have to evaluate the integrand, that f of x0, f of x1, f of x2, at those 3 different points. Okay, so let's do that. I'll change to red, the good old math color. And I'll say that this integral is approximately equal to, and then I need h over 3, so it's 0.5 over 3, and then I'm going to multiply this by f of 1 plus 4f of 1.5 plus f of 2. And if we can evaluate those 3 things, we're good to go, okay? Our function is sine of x over x, so it's not a terribly hard integrand to work with. Again, just make sure by convention we're working in radians. This turns out to be, let's just fill in the functions to begin with so you'll know where everything comes from. This is going to be nothing more than the sine of 1 over 1 plus 4 times the sine of 1.5 over 1.5, and then plus the sine of 2 over 2. And if you key this in really carefully and you work it all out, I think in the end here, this gives an answer of about 0.56. There, it looks like a 6. 0.65935. Okay? If you are interested, the true value here is actually 0.65933. So even with a pretty big h, right, h equals 0.5, we get a pretty good approximation. We're approximate to within, what, a 10,000th, which is pretty darn good, okay? But it's that simple to use. It just means that we have to know another formula. I will expect you to know it, okay? But once you know it, it's really no harder to use than the trapezoid rule was from before, okay? I'd ask if there are any questions, but we're not in lecture, so if you have any questions, just let me know in the comments or in an email. But we're actually going to go from here and extend this. So let's move on. And, you know, when you extend it, a lot of textbooks will tend to call this Composite Simpson's rule. It's I don't know, unnecessary. I just always called it Simpson's rule, but understanding that if you have more points than 3, then that's just what Simpson's rule looks like with those points. But it's actually a really simple concept. All we really have to do is take the idea of approximating a function by a parabola and then daisy chain it forward. So if I have 3 consecutive points and I have a parabola over those, and then I have the next 3 consecutive points and I do a parabola over those, and so on, and I put them all together, I can get a good approximation here, a good approximation there, a good approximation there, and add up the results. That's really all it is, okay? But it yields a funky formula, like a really interesting formula that I kind of love because it's just kind of quirky, okay? But we're going to develop it. It's not hard at all, okay? Yeah, so we need a couple of considerations along the way. Um, yeah, we need, as I said, subsequent sets of 3 points rather. Okay, so we need, of course, polynomials. So just changing back to my blue color here. Um, Polynomials that lie above two subintervals, but essentially, you know, around those three nodes, that parabola might be in many cases a really good approximation of the function, but I want to keep that approximation as I go forward, right? Beyond those three, maybe it goes away from the function in general and so on. So my next parabola I want to consider actually uses the third node as the new first node. And so the first 3 points will be approximated by the first parabola. And then I'm going to take points 3, 4, and 5 and find another parabola. And then I'm going to take points 5, 6, and 7 and use another parabola. And so you see every second point is going to be involved in 2 calculations, which is a little bit interesting, okay? That means that we have to have a particular number of subintervals, right? I need to make sure that there's an even number of subintervals because I need a parabola to be over every set of 2. So set of 2, set of 2, set of 2, set of 2. I need an even number of subintervals to make sure that I can define this really well, okay? So we'll consider only the case where you have an even number of subintervals. You might be able to find some interesting hybrid strategy of dealing with an odd number of subintervals, but then why not just divide it into an even number to begin with if we have the freedom to choose the h, okay? Having an even number of subintervals means that we require an odd number of points. Thinking about why that is, imagine if we had 2 subintervals, that means we have 1, 2, 3 points. And the 3 points, like we had in the last example, like x0, x1, x2, define 2 subintervals. And similar for if we wanted a larger number of if I wanted, for example, 4 subintervals, I would need 5 points. 1, 2, 3, 4, 5. If you draw them out, then you can see it, I guess, pretty easily. Or if you imagine, I could do it right here, right? If I have 1, 2, 3, 4, 5, I have 5 points. So, and the number of subintervals I would have here would be 1, 2, 3, 4. So having 5 points would make 4 subintervals, and similarly having n points would make n minus 1 subintervals. So if I have an even number of subintervals, which I need an odd number of points, which probably was obvious to begin with, so I don't really know why I spent another 2 or 3 minutes describing it, but now you should be really, really comfortable with that idea. Okay, so as I said, the formula is very interesting. You can derive it from scratch, but it's extremely tedious, right? It's actually tedious enough. Whoops. It's actually tedious enough to do just the 3 points, right? And to extend that to a larger number is even worse as a job. So again, kind of like the similar, I'm going to take the easy way out, just present the formula and explain it to you. So check this out. There's our integral, a general definite integral. And I partition this between x0 and xn, okay, stretching from the a and the b, the domain of integration, okay, giving us an even number of subintervals, okay. So we're making sure that we have an odd number of points, even number of subintervals, and as I said, we're going to continue making a chain of different Simpson's rules, so that the last node of each set becomes the first node of the next one, and chaining it together until I get to the end. So this is what we get to. Ready? And you almost have to sing it. I'm not going to sing it. I might kind of. I don't know. The integral has an h over 3, which seems kind of familiar from before. And if you imagine, our formula from before went 1, 4, 1. Okay? But if I take, so f of x0 plus 4 of the middle one plus 1 of the third one, right? But if I'm going to take that and I'm going to add it to the next 3, then that f of x2 is going to appear again, right? I'm going to get an f of x2 plus 4 f of x3 plus f of x4. And so that f of x2 is going to appear twice, once from the first set and once from the second set. And this is actually going to happen with every single one of the interior points that happens every other, right? Everything that wasn't multiplied by 4 ends up being double counted if it's not one of the endpoints. So you get this bizarre kind of formula that jumps back and forth between 4 and 2. So you get f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4, and so on and so forth until you get to the second last one. Oh, look at sorry, I just got a notification there. Let's get that out of there. You get to the second last one, it's 4 of that one, and then back down to 1 for the last one. So you have this weird pattern that is completely justified when you think about it, that goes 1, 4, 2, 4, 2, 4, down to 1. Okay? And you keep bouncing back and forth between those in all of the interior points. You multiply the result by h over 3. And that is what Simpson's rule looks like when you extend to more points. Okay? So we're going to take that. I'm going to just put a box around this and say, this is Simpson's rule for n greater than 3 points. And you should know how to use that too, okay? We're going to apply that to a last example, but I did want to note, right? It's a little bit weird to write this out 1, 4, 2, 4, 2, and so on. With a dot, 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 you need to include a lot of terms to get the pattern down. You can write it in terms of a sum, like summation notation, like I have at the bottom of the screen right now, but I think it's a little bit awkward. I think it's easier to look at the formula above and figure out what that's saying than try to muck through a formula like the one that I have at the bottom of the screen right now. So, I mean, as long as you're good with one of them and you understand how the pattern works, you should be good. Okay? We're going to use this in an example, and we're going to return back to our error function from before. This is the error function evaluated at 1. Again, this is a special function that you cannot figure out by using direct integration at all. So let's remind ourselves of what that is to begin with. So the error function at 1 is that 2 over root pi scaling factor, and then the integral from 0 up until 1, right? 1 goes right there. E to the minus t squared dt. Okay. Again, I can't evaluate that directly. I have to use a numerical integration technique. And here we're going to use Simpson's rule. We used trapezoid rule last class to do the error function evaluated at 2, right? ERF of 2. And we got a pretty good result here. We're going to get a very good result here as well. We have 4 equally spaced subintervals. So if you imagine taking 0 to 1 and dividing by 4, we're going to find that each one has to have a width of 0.25. So 4 equal subintervals. Each will have width of 1 minus 0 over 4. So you can use, it's going to be 0.25 or, well, a quarter. And I'm just going to outline again what those points are on the side. So we have x0 equals 0, x1 equals 0.25, x2 will be 0.5, x3 equals 0.75, and x4 equals 1. And those are going to be our set. You can see the even number of subintervals here, the odd number of points, and that will let us use our formula. Okay, so let's just jump in and do this. I need my red, and we're going to say down here that ERF of 1 is going to be approximately equal to, using Simpson's rule, okay, h over 3, so that's going to be 0.25 over 3. And let's see here. I need to take this thing. That has the 2 over root pi scaling factor out front. So I'm just going to write this out front, I guess. So 2 over root pi, I guess, should go out front, because the integral is what I'm trying to approximate here. And then let's see how this works. H over 3 times, and it's going to be f of 0. And then think of that, well, song or the pattern, right? I need 1, 4, 2, 4, 1 in order to do those 5 points, right? So that's going to be plus, oh, see, I screwed this up. I need 4 f of 0.25 plus 2 f of 0.5 plus 4 f of 0.75 and then plus f at 1. And that should do the trick. So I'm going to write this out just so we know what we're calculating here. I'm going to just simplify this factor. I see that 2 times 0.25 is, well, a half. So I'm going to write 0.5 over 3 root pi. And then just write this all out. So this is going to be e to the minus 0 squared plus 4 e to the minus 0.25 squared plus 2 e to the minus 0.5 squared, and then 4. It's easy to like tune out and just start going on autopilot, but just make sure you don't lose track of what you're doing. It's very easy to do. And I'm evaluating that integrand at each one of those points. You work this all out, and I think the calculation comes out to about 0.84274, which you could double check for me if you wanted to, but I'm pretty sure that that's right, because if you jump onto a math tool or whatever and actually evaluate this, it's funny because, right, a lot of these programs and so on, like Maple or Wolfram or different kinds of mathematical software, they're really using numerical techniques to get a better approximation, right? Because all we're able to do is really approximate it. But I get an actual result there, as close to actual as we can get, of 0.84270. Again, really good. Okay. So yeah, that's how it works. It's pretty cool. You get to a method that has this interesting formula, but once you know the formula, it's really not any harder to use than any of the other formulas we've talked about. Okay. I just want to end by talking a little bit about some error associated with all 3 of the techniques. There is a general error bound for this. It's kind of crummy. I instead wanted to kind of go back to the beginning of the course when we were talking about order of error as a parameter heads to 0. Here a parameter is really the size of the step between individual nodes, which we've called h. And so I want to know what the order of the error is as the h goes towards 0. Right? I want to emphasize that when it comes to error and order of error, right, all 3 of these techniques, right, Riemann sums, trapezoid rule, Simpson's rule, the error approaches 0 in all 3 cases as h goes to 0. That's not a question, right? But the order of the error determines how quickly that happens, right? Remember that the order of the error tells us how quickly the error decreases when we decrease the size of that h, all right? And it might decrease linearly, or it might decrease quadratically. There are lots of different ways that this can happen, okay? So just to reiterate, I know that that's been something we've talked about a few times through the semester, but I always want to make sure that everybody has that understanding of what's really going on here. So the error shrinks to 0 in all 3 methods as h goes to 0, but it decreases on different orders. If you do the math, you can figure this out, actually relating to some of the error bounds that we found before. You can find that Riemann sums produce a linear error. So big O of h, as in if I decrease the step size, okay, the error associated with doing a left or right Riemann sum decreases linearly, okay? So like by some multiple of that h typically. And the trapezoid rule, on the other hand, produces error that is on the order of h squared. So it reduces quadratically. That is, if you halved the step size, then the error is likely to decrease by a quarter, right? Or by 3/4 rather. So 1/2 is going to be associated with an error that decreases more quickly than linearly, okay? And so with Simpson's rule, the one that we just did, you can actually show that the error, and we saw the two estimates that we had up there were very, very accurate. But as a matter of fact, that accuracy improves much more quickly as well as h decreases. it's actually got an error that is on the order of h to the 4 as h goes to 0. Okay. So as I said at the beginning, we just covered a few of the uh, typical methods that are talked about in a numerical methods course. These are all fairly simple and pretty easy to justify. Some of the derivations are a little messy, and that's okay. There are methods that go beyond and that might be useful in different kinds of schemes, okay? And you're welcome to explore one of those potentially in your project if you find anything kind of interesting. Um, there's other adaptations you can do, like you might have a variable step size, in which case you have some interesting adaptations to the formulas you might be able to consider. That could be really useful to get a more accurate estimate where the integrand changes, I want to say especially quickly, right? Because imagine that you have a function that is, more or less doing its thing, but then has one quick spike and comes back, right? If I have a function with one quick spike, then maybe if I only have big wide rectangles, it's going to do a really bad um, job at approximating the true area. And that might be true even if for most of the domain, the rectangles or trapezoids or whatever we just did right here would do a pretty good job on regions where that function is not changing very quickly. But where it's changing very quickly, maybe it would be better to sample that function over many more nodes during the duration of that spike. That way you can add up smaller bits of area that more accurately represent the shape of the curve. And so you can do this kind of thing, blending techniques or having what are called, adaptive approaches, adaptive step sizes, and so on. Okay, so that about does it for this topic. And all of this material will be covered in a lot of depth on the exam. So make sure that you know it really well. And again, let me know if you have any questions. I hope you've enjoyed and found these lectures to be pretty useful. It's been different for me, but I've had a lot of fun putting them together. I just want to say good luck with the rest of the course and your other courses. And hopefully, the next time I see you, we're all back at on campus and life has returned to something resembling normal. All right? Take care of yourselves, everybody.